This is how to derive the formula for continuous interest or continuous growth, and also Euler's number E. Just a heads up, I was not able to derive the final standard formula for continuous interest, but I was able to come up with another formula that gives the exact same answer, and I wasn't able to bridge that gap between my formula and the standard formula. But this is what I got so far, and I hadn't seen this posted when I searched for it, so this is what I'm going to show. And this little project I'm showing right here, or this video, is a good example of what this channel is about. I like to take formulas or take things that are unfathomable for most people, and they just look really complicated, and I like to be able to figure out how to derive the formula and then show it in a video and make it look really easy. So that's what I did here. I tried to make it look really easy. I think it's sort of easy. It involves just high school algebra, so yeah, it's not bad. Okay, so pause the video if you want to figure it out for yourself. Otherwise, I'll show what I got. First off, let's say we're going to take a loan for 1 year and calculate the interest just once at the end of the year. So let's say it's 2% APR, or annual percentage rate, which means we borrow $10, and then we take that plus $10 plus the 2%, and that equals $12. So this is what it would look like if we just borrowed money and it was a really simple interest calculation and you just calculated the interest once at the end of the year. The formula looks like this. It's principal plus your principal times your rate equals the amount that you owe. Then what we can do is pull out the P right here with the, what do you call it, distributive property. When you pull something out, I don't know what reverse distributive property is. But at any rate, we got principal, and then in parentheses is the quantity 1 plus rate equals your amount. I guess I'll turn that into an M-O-N-T right there. That's what you owe at the end. Okay, next page. Okay, and then right here, I wrote APR for the annual percentage rate, but that's not really needed. Let's do the interest calculated twice. So we have our principal plus our principal times the rate over 2, and that'll equal the amount after the first 6 months. So this is where I was going to say it's like a 2% APR. But then what we have to do is take that 2% and break it in half, because we're going to calculate it twice. So it'll be 1% over the first 6 months and then another 1% over the next 6 months. So that's kind of where I was going with this when I wrote the APR. But anyways, it looks like this: principal plus your principal times rate over 2, because we're calculating the interest twice throughout the year. So it would be that 2% turns into 1%. That equals the amount that you have to pay after the first 6 months. Then we take that amount for A, we take A plus the same amount times rate over 2, and that gives us B, and that's what we have to pay at the second 6 months, or when the year is up. So the formula looks like this. We can pull out our A, and we get A times the quantity 1 plus rate over 2 equals B. The tricky part about deriving formulas is you have to keep things in the same form, or you don't have to, but it's just a lot easier if you keep your equations in the correct form until the exact right moment. Because if you go pulling terms out too soon or too late, then it can make it more complicated. And this is one of those situations. So right here, I found out it's easiest if we pull the A out at this part, and then I'll go to the next page. And previous page on the left, new page on the right. So here's our amount times 1 plus rate over 2 equals B. But now let's turn that A back into principal. A equals principal plus principal times the quantity rate over 2 right there. And then we bring down our 1 plus rate over 2 right there. Notice what we have now is principal times the quantity 1 plus rate over 2 squared. And that's because that rate over 2 is because we're calculating interest twice during the year, so there's 2 divisions. And then we're squaring it because that's just what the algebra says we're supposed to do. So the formula looks like this: the genericized formula, principal times the quantity, 1 plus rate over number of divisions, quantity to the number of divisions equals B. And that's what you have to pay. Here's where I made a little error the previous time I posted this video. This formula right here would only work for 1 year. If you want to take out that loan for 2 years or 5 years or whatever, then this formula doesn't work, so I'll have to modify that. This is why I do these videos also, because I always pick up little nuances like this. And next page. Okay, right here I just showed what happens if you what did I do here? If you don't pull out your terms at the right time, it just gets more complicated to derive this. And I wanted to show this because this is the first way I did this, and this was more complicated. So I have the same right here, principal plus principal times the quantity rate over 2 equals the amount. I got the amount plus amount times rate over 2 equals B. But I didn't pull out the A here. What I did is just turned A into principal plus principal times rate over 2. Now I've got this big mess right here I have to deal with. I can pull out my principal plus the principal times rate over 2, and then I get the 1 plus rate over 2. Actually, but then I have to pull out principal again. Anyways, as you can see, it's the same derivation, but it's just more complicated when you do it this way. So I just wanted to show this because this is kind of it works, but it's the long way to do it. And I mentioned this also on deriving this when I was doing my Tower of Hanoi formula. I found out with that I was pulling out terms too soon or too late, and I just came up with this big convoluted mess. So the tricky part is a lot of times is just being able to pull things out at the exact right time, and it just takes some experimentation to do that. Just keep reworking the formula over and over and doing it a different way each time, and eventually you find the easiest way to do it. So that's what I did. Okay, next page. On these 2 pages, I wanted to really illustrate the pattern that the exponent indicates how many times we have calculated interest. So for example, if the exponent is 3, then that means we have calculated interest 3 times. So this is how we can show that. You just take your principal plus the principal times the rate equals the how much you owe over a certain period. But here I'm going to divide the year up into segments of 3. So January, February, March, and April will be one segment of the year. So if we have a 3% interest per year, which is a 3% APR, we take 3 divided by 3, which equals 1, which means we only charge 1% interest over that first third of the year. So we take our principal plus principal times rate over 3 equals A. Go ahead and pull out our P's early on. Now that we've solved for A, let's solve for B. So it'll be A plus A times the rate over 3 will equal B. So there'll be another 1% interest right here. And this will be over the second third of the year. So this will be for May, June, July, and August. Go ahead and pull out our A's early on here. So A gets pulled out here. We end up with 1 plus rate over 3 equals B. Now we can go ahead and substitute in what A equals. A is the principal times 1 plus rate over 3 right here. So A just goes down to here. We bring down our 1 plus rate over 3 here. We combine this and this so we can square it. So we end up with principal times 1 plus rate over 3 squared equals B. That 2 on the exponent also means we've calculated interest twice. Now that we've solved for B, let's solve for a C. We do the same thing, bring down our B here, pull out our B's, and then we go up to here. We substitute in what B equals, and B equals principal times 1 plus rate over 3 squared right there. Bring down the 1 plus rate over 3 to get C. And we end up with principal times the quantity of 1 plus rate over 3 to the third power, because this is our third calculation. So maybe you can see with a little bit of effort, you can follow along and derive this yourself. And that's if you pull everything out early and do it in the right order. But for example, if you didn't pull anything out and you got all the way down here to this last step, you would have a long string of terms and it would just be a big mess. Okay, next page. Okay, so here's the last 2 pages, and this is how you have to modify it if you're doing a multi-year loan. In this case, I'm going to take out the loan for 3 years. So what we have to do is pretend that there's 36 months in a year. So if you say 2% APR or annual percentage rate, then actually you have to multiply that times 3, so it becomes 6% for 3 years. And then the formula works out. Like I warned at the beginning of this video, this formula is a little bit messier. Well, I don't know if I warned on that part, but it's not the same formula as the standardized formula. But this, again, like I said, this gives the exact same answer. So let's take out a $100 loan, that's a principal, times the quantity 1 plus the rate. Now we take the rate, which is 2%, but we have to multiply that by 3 years because we're gonna take out the loan here for 3 years. And then we divide that by the number of divisions. Let's divide it up 1,000,000 times, 1,000,000 divisions per year, and we're gonna do that over 3 years. So we'll end up with 3 million divisions. So we take that total number of divisions, put that up here as an exponent. We got 3 times 10 to the 6, or 3 million divisions. But notice what we have here when we genericize this equation. We have year divided by year, so that will cancel. And I do mean cancel because they will disappear. So what we have is principal times the quantity 1 plus rate over number of divisions per year. Take that to the total number of divisions, which is equal to the number of years times division per year. Notice when you multiply year times division per year, year divided by year will cancel. You're just left with divisions. So I guess I was showing on the wrong equation right here. But anyways, this is what it looks like right here, and that's the final amount. So let's take this $100 loan. Let's do my method here on this formula I just derived. We get this big long mess here. And remember, I did it to a million divisions, which will take it out to about the millionths place on the millionths decimal place. So it goes tens, hundreds, thousands, 10,000s, 100,000s, millions. And then I guess what is this here? 10 millions, 100 millions right here. So this is the answer I got. It takes you out to, you get your first arrow at the 100 millionths position, or 100 millionths decimal position. If you use the standard formula of principal times E for Euler's number, take that E to the exponent rate times time, then you will get the same answer. But instead of the 2 in the 100 millionths decimal position, you'll have a 5. Actually a 6 because it rounds up. So what did I say here? What this looks like here, if you take the limit as the number of divisions approaches infinity to this equation, then you'll get your amount. And this looks really similar to Euler's number, which is as n approaches infinity, 1 plus 1 over n to the nth power. But here's the difference on the formula. Here you have Euler's number to the RT, and on mine I have the rate right here, the R, in the numerator of this fraction. So I didn't take the rate to an exponent like they did, so I don't know how to bridge that gap to go from here to there. But the reason I'm posting this video is because this is more information than I had seen anywhere else on how to derive Euler's number or how to calculate continuous interest. So I thought this was kind of fun, and I had fun doing this. And also I cleaned up a little error from my previous video when I posted this, because on my previous video I thought this formula worked for any number of years, but it turned out it only worked for 1 year because I had to multiply the numerator here by 3 if I went for 3 years. So cleaned up a few little errors. Hopefully I explained this a little more concisely than in my previous video. So yeah, that's pretty much it. I'm going to throw in a couple of quick addendums. First off, I think at one point I accidentally called E Euler's number instead of Euler's number. And that's because I went to college back in the 90s, which was mostly pre-internet. And so that was what people were calling it back then. So I still tend to do that out of habit sometimes. And also this E, it also represents growth. I don't know if it's like bacterial growth or something. I don't remember. It's been a long time since I looked into it, but yeah, I figured this is good enough for this video.